So, what's really going on inside the brain of a self-driving car? It's not some single, simple mind. It's more like an entire orchestra of artificial intelligence. Today, we're going to pull back the curtain on the incredible, super complex management it takes to actually conduct that orchestra and make sure it all works safely. Let's dive in.
Right, so this is the big question, isn't it? How on earth do you manage an AI that's smart enough and reliable enough to navigate our chaotic streets? And let me tell you, this is not just a coding problem. It's a massive, high-stakes management challenge. It's a whole new kind of symphony, and it needs a conductor.
So, you got to throw out that idea of a single AI brain. It's just not how it works. Think of it more like a symphony orchestra with hundreds of highly specialized AI models, all playing their individual parts. And just like any orchestra, it desperately needs a conductor. In the world of self-driving cars, that's the Technical Program Manager, or TPM. Their job is to make sure every single note is hit perfectly, and most importantly, safely.
So where does this whole story begin? Well, with AI, it always starts with data. But we're not just looking for tons of data. We're on a quest for smart data.
Okay, the first key concept you have to understand is something called active learning. These cars generate a mind-boggling amount of data. We're talking petabytes, way too much for humans to ever sift through. So the system itself has to be smart about how it learns. It needs a strategy to automatically find the most interesting, the most confusing, the most informative moments to actually learn from.
And here's how it works. It's this continuous, self-improving loop. So the cars are out there, driving around, recording everything. Then, back at the office, other models are crunching through all that raw footage, basically panning for gold. An algorithm flags what it thinks are the most informative little clips. Those clips then get sent to human experts. These people, the annotators, label the data, teaching the AI what it saw. And then, this is the magic, that new labeled data gets fed back into the training set to make the models even smarter. And the whole cycle just starts all over again.
So what makes data informative? What is the system actually looking for? Well, it's hunting for a few key things. First, moments of uncertainty. Where the model saw something, but its confidence was low. It just wasn't sure. Second, edge cases. That's the weird stuff. The bizarre construction vehicle it's never seen, or a sudden freak hailstorm. And finally, and this one's really interesting, disagreement samples, where two different AI models looked at the exact same scene and came to different conclusions. That's where the real learning happens. And this is where the humans become absolutely critical. After the AI flags all these tricky scenarios, human annotators step in. They are the teachers. They painstakingly label every single thing, every pedestrian, every car, every lane line, correcting the AI's mistakes and teaching it the kind of real-world nuance that a machine just can't figure out on its own.
Okay, so we've found the smart data, we've trained the models with it, but how do we actually know we can trust them? I mean, really trust them with our lives? That brings us to the next crucial phase, testing.
And this right here is the fundamental challenge. With normal software, like the calculator on your phone, things are binary. 2 plus 2 is 4. It's either right or it's wrong. Simple. But with machine learning, correctness is statistical. The AI isn't 100% sure of anything. It's all about probabilities and confidence levels. It's making an educated guess, and that changes everything about how you test it. So to measure this new kind of performance, engineers use a whole suite of metrics, and they usually fall into 3 big buckets. First is perception. Basically, can the car see the world correctly? Second is prediction. Okay, it sees things, but can it guess what they're going to do next? And third, planning. Based on all that, does the car actually make decisions that are not only safe, but also comfortable for the people inside?
This quote absolutely nails the heart of AI safety. It's not enough for a model to just say, that's a stop sign. It needs to be able to communicate its own certainty. It needs to say, I'm 99.9% confident that's a stop sign, or, just as importantly, I'm only 40% confident that's a person. Knowing what you don't know is maybe the most critical skill for a safe AI. Because the consequences of getting this wrong are very real. If a model is overconfident and poorly calibrated, it might slam on the brakes for a plastic bag it thinks is a child. That's a false positive. Annoying, but not catastrophic. But what's worse, if it's underconfident or just flat out wrong, it could miss a real danger entirely, a false negative, and that's the nightmare scenario. It's an incredibly delicate balance.
So let's say a new model has passed all these insane tests. Now what? How does it actually get from the lab into a car that you or I might ride in? Well, the process is, as you might guess, painstakingly cautious.
It happens in 2 major phases. First up is offline testing.
This is where engineers can replay millions of miles of previously recorded drives and see how the new AI would have performed. But you can't live in a simulation forever. The next step is online testing, and this often starts in what's called shadow mode. The new AI is running in a real car on real streets, but it isn't actually driving. It's watching and making decisions in the background, like a student driver silently comparing their choices to the teacher's.
But there's this constant enemy that makes all of this so difficult. It's called dataset drift. The real world is never static, right? There's always new construction, the seasons change, a new brand of electric scooter suddenly becomes popular. The data the AI was trained on can get stale, fast, and its performance can degrade in subtle ways if it's not constantly being monitored and retrained for these shifts.
Now, I want you to just look at this number for a second. 0.01%. It looks impossibly small, almost meaningless.
But in the world of self-driving cars, a performance drop, a regression of even that tiny amount can be a massive safety red flag. Finding a regression that small is enough to bring an entire deployment to a screeching halt, sending engineers scrambling for weeks to figure out what went wrong. The standard for safety is just that unbelievably high.
And here's the kicker. Remember, all of this intense testing and extreme caution, it's not just for one AI model. It's for the entire orchestra. We're talking about juggling hundreds of these brains all at once.
I mean, just look at this list, and this is just a tiny sample. There's a model whose only job is to detect objects, another just for finding lane lines, one for recognizing traffic lights, one that does nothing but try to predict what a pedestrian is about to do. They are all hyper-specialized, and they all have to work together perfectly in real time.
And this is the ultimate challenge for our conductor, the TPM. All of these models are deeply interconnected. The part of the brain that plans the route depends on the part that predicts other cars' behavior, which depends on the part that sees the world. So if you upgrade the car's eyes, say a new perception model, you could accidentally and catastrophically break the decision-making part of the brain downstream. It's a domino effect.
So the TPM is the person who has to oversee this entire massive life cycle for every single one of those hundreds of models, from the second the data comes in from the fleet, all the way through annotation, training, evaluation, deployment, and then monitoring its performance in the wild, which, of course, creates feedback that starts the whole loop over again. It is a monumental task of coordinating.
So in the end, it all comes back to that human conductor leading the AI orchestra. It's their job to make sure every single model is in tune with every other one, that the tempo of development is right, and that the final performance on the road is nothing less than perfectly safe every single time.
And that really brings us to the final thought I want to leave you with. We've just spent this time unpacking the immense, mind-bending complexity of managing the AI inside just one car. So the real question is, what does it take to scale this up? What does it take to manage and conduct a fleet of thousands of these AI orchestras all performing live on our streets all at the same time every single day?